we have inductive kickback. As the name suggests, what is the inductive? Whenever when you see the inductive, what comes into your mind? Coil, right? That makes sense? The coil. So inductive kickback just as you use your hand, use your feet to kick back somebody. What is the inductive kickback? We want to learn how to use this is how to implement unidirectional and bidirectional control for this is the DC motor. And the third objective is that we want to know what is the pulse width modulation PWM. What is the pulse width modulation? And how can I just change the speed of the motor using this is a pulse width modulation. So these are three very important ones. Here, this is an inductive kickback. So what is inductive kickback? As I said, whenever you see the inductive, the first thing coming to your mind is a coil, right? So the coil here, because the last time I told you guys, all this is this generator, all this motor is a generator, and all the generator is a motor. And because just as electrical, magnetic, and they are two sides of the same coil. So these two guys are always together. They're the twin, are always together. If you have electrical, you have magnetic. If you have magnetic, you have electrical. So because the motor, when the motor works, and there is electromotive the force, we can that model can be simplified as this coil, resistant, and electromotive force, which is the voltage. And so as a result, so whenever so when this is a DC motor is working, everything is fine. Everything is fine. However, when you stop, this DC motor, and you will have a problem here. And this inductive kickback means that a large voltage spike, very high at the peak, that occurs whenever the current flowing through an inductor. Inductor means a coil. The coil, okay? Inductor is abruptly switched off, and it can result in dysfunction of the drive circuit components if not handled correctly. So when there is a current flowing the coil, it works very well. Suddenly you cut off the current and you will have inductive kickback. So this is inductive kickback, the concept. So this one can, and this figure shows two ways to control the current through a motor, right? The current through a motor. And first one, we have a DC motor, and we have a power, so we have a switch. The second one is very similar, but we use different device for the as a switch. And now this time we use a solid state device, and we use this is a transistor, NPN transistor. The same thing, okay, same thing. You just turn it on, and this guy works. And also you just adjust the input value and to make sure. And so this is the voltage difference between this terminal and this terminal is greater than the threshold value of this transistor, and then this guy can work. So the same thing, the same mechanism. And now both of them here, both of them do not have this is the mechanism to handle the inductive kickback. And then what will happen if you turn off the power? What will happen? And you will get this figure. So first one here, so this is time and this current, so this is time and voltage. So how this shows on how the current changes. So that one shows on how the voltage changes. Okay, when it goes for this one, and the current goes here and then stable, and suddenly you cut it off. If you cut it off, the current goes from highest point and to very low, almost zero. So this is for the current. And however, the corresponding change of the voltage is totally different. You can hear, okay? So as long as this is working very well, so working. So here is very stable. And however, at that instant, when you cut off the current, and you will have a so high this voltage spike. It can go to 250 volts. Then after some very short time, it goes very, very low. And so, do you have an idea what kind of the consequences, and you will see if the current goes on from this is 5 volts or 12 volts or maybe 36 volts and to 250. So these 250 volts can penetrate almost every the devices on the circuit boards. So this is very, very dangerous. It's very, very bad, destructive. It's called destructive. You understand, guys? So you can see these two figures. For this one, it goes very, very smoothly. I mean, not the abrupt change, but that one, the voltage there, the resultant voltage is kind of horrible. So this one voltage can penetrate almost all these is the components, and even though this voltage just lasts very, very short time, so we need to find a way to handle this. Okay? And how to handle, and we have several means. So before we talk about this is the several mechanisms, and we talk about the components. The first one, diode. And you guys have ever heard of or heard diode, guys? Diode is the simplest electrical component, and the diode says that you can see. So this is this is diode, okay? That diode components. And so if you have cathode, let me put this way, the figure is not right. So this is a diode. This is my diode. So if this is a positive and this is a negative, and I have current. And however, if you just switch the direction of the voltage, if you have this is negative, this is positive, so this is anode, this is cathode. And so here is almost no current. And so this current almost equals 0. Understand, guys? So that means for this guy, only in one direction, the current can go through. In the opposite direction, the current is cut off. So here, this figure shows, look at this one. This is a forward bias. It's called forward bias. This is a cathode. This is an anode. If this is the case, you can have the current. The current is the current can go through. And however, here, look at here, if you have reverse bias, this is a minus, this is positive. You can see, and this goes this way, and you can see also the magnitude is nanoampere. It's almost negligible. You understand, guys? So for this diode, so this is wrong. I'm sorry, guys. This is a cathode. This should be cathode. This is anode. So for this diode, just keep in mind that, and so for this guy it only allows the current goes in one direction. Pay attention to how to just wire this up, and pay attention to the cathode and pay attention to the anode. Questions regarding this one? Questions? No question? So this diode, next one is a Zener. So you can see the Zener is very, very similar. The sign there is very, very similar to the diode, except so this one. Okay? So it means that for the forward bias and the same thing, and for the forward bias and for this one, and it also goes in one direction here, and it goes in one direction. And however, and for the reverse bias, and we have a very, very beautiful this voltage, this characteristic we can use. So here, okay, it can go there VZ here, And so this VZ will be stabilized. The VZ is a constant. And then how can we use this one, guys? We can use the Zener. We can use the Zener to stabilize the voltage. You understand this? As long as you just wear this Zener using this reverse bias, and you can use this Zener as a voltage stabilizer. Questions? Questions, guys? A stabilizer. What is a stable? This is a stable voltage. You need to look at the data sheet and from the vendor. So this is a VZ. Now, after we have learned these two important components, the diode and this is the Zener, then we come back and to see how can we handle this inductive kickback. So inductive kickback here, let's see. So this is our previous one, except this one. So we have power DC motor and this NPN transistor, which serves as this is a switch. And so you can see here, okay, if I have a voltage, if I have voltage, then suddenly this guy, when this guy is shut off. However, if I just give this is the route, and for the current that is still in this is this is a coil, and then so this you can see the current can go this way. So this current can be released.
Is inductive kickback something that we can encounter anytime we hook up a switch to a DC motor?
You see again?
Is inductive kickback, is that something that can happen anytime we connect a DC motor to a switch or a transistor?
Yes.
Okay.
Whenever you cut off the power, cut off the current, and you will have inductive kickback, the spike for the voltage.
Thank you.
So this voltage must be handled. Okay. So you can look at it here, and we just add a new route. So this route allows the current in the coil to be released. If you release it can go this one, it will not have very high voltage. So as a result, the components on the board will be saved. You can see, so this is the characteristic, the curve. Suppose this is the time when you cut off the power, when you cut off the current. So you can see go only from 0 to about 13, less than 13 volts. Less than 13 volts is a safe volt. It will not damage the majority of this circuit board. You can see the 13 from 250 and to about the 13 is a huge change, right? So this is our first mechanism that we can use to handle this inductive kickback. I want you guys to write down. So this one will be tested. So I will ask you what is the inductive kickback, and then I will follow up on how many mechanisms we can use to handle this inductive kickback. This is our first mechanism. This is our first method. The second method, you can see the second method. And second method is we add diode, and then we just add another component, the transistor. Right? I'm sorry. Yeah, this is a transistor. This is a transistor. This is resistor. This is a transistor. We add a resistor here. So this resistor, okay, this resistor can carry, can reduce. This is the voltage. Why? Because when the current goes through this resistor, and there is a voltage drop on it. So you can see this is the curve. So on the left hand side, and here is the curve. So you can see that the resistance increases under dissipation, and the kickback spike will be dissipated by a factor of 2 faster than the diode alone. So this is our second mechanism. Right? Our first mechanism is diode alone. So the second one is diode plus a resistor. This is our second one. And third one we add. Third one we add both this diode and Zener. And as I said, Zener is specialized is a diode. So if we add these two guys together, and we know that, and so this is this can also handle this inductive kickback. So this is the third mechanism. So the more rapidly we can turn off the current flow through a motor, the better. So here are the comparison of this is several mechanisms. The first mechanism, diode alone. You can see diode alone. First mechanism, diode alone. And second one, resistor plus the diode. Second one, and the third one is Zener only. Is Zener only. The farthest one is the diode plus Zener. So this one is the best one. What? So as I said, and I will ask you, and use your own language to tell me what is inductive kickback is, and then how can we handle? What are the commonly used mechanisms? So there. Then we talk about bidirectional control of motors. Last time I told you guys how can we control the direction of the motor? Because the motor, this is the motor out to the shaft, and we can just let it rotate clockwise or let this guy rotate counterclockwise, right? And how can we control the direction of the rotation? We change the direction of the current. If we change the direction of current, the direction of rotation of the shaft out to the shaft will be changed. So here, that means we need to know how to change the direction of the current. So here, guys, look at this one. So here is input the counterclockwise. I'm sorry, clockwise. So this is input counterclockwise. And what does it mean, guys? So here is the positive volts, and so here is the negative volts. So these two guys, this is the diode and this diode, and they are used to handle the kickback, inductive kickback. So you should know the function of these two diodes. And so here is a PNP and NPN. The last time I told you guys how this NPN work and how this PNP work, right? How this is NPN work? This NPN, you can see this is the emitter. So this is the gate. So this is the collector. So this is the base. Okay. If the voltage difference between the base and the emitter is greater than the threshold value, and then this guy will open. I'm sorry. And so this guy will have current. Will allow the current to go through. What? So I can control this voltage. If I just increase this voltage value to make sure that the voltage difference between the base here and this is 0 for this one, which is a ground, minus V. This is minus V. For this minus V, this is ground. I'm sorry, this is ground. This is minus V. If the voltage difference between this base and this is emitter is greater than the threshold value, and then the current will go this way. Guys, look at me. The current will go through this DC motor from this is 0 to the negative. That means from the right to the left. Right? You guys agree? So that is one direction of my motor. And however, if I just shut off this one, so for example, I just let this guy to be very, very low. And as a result, this NPN does not work. And then I let this guy work. I let this guy work. How can I let this guy work? The same thing. I just want to make sure the voltage difference between the base and this emitter is bigger than a threshold value. And then the voltage, the current can go through this way. Okay? And then go this way. That means from the left to the right until it reaches this ground. So as a result, and by controlling these two guys, I can control the DC motor. Are you guys following me? You're following me, right? Okay. That's good. So as I said, if we want to control the DC motor's rotational direction, and we need to control these guys, the current direction. So let me ask you guys, what are the function of these two diodes? I just forget. Can somebody remind me what are the functions of diodes? Ethan. You name it Ethan?
My
Yeah.
Aiden.
Aiden.
To just let current go through only one direction.
What is the function of these two diodes here?
Oh, these if there's inductive kickback.
Okay, to handle the inductive kickback, because we have the direction, we have two directions of the current, so we need to take care of both of these two directions. That's the reason we use two diodes separately. Good, very good. Now look at this one, guys. So this is a typical H-bridge circuit. Have you guys ever heard the H-bridge circuit? And why this guy is called H-bridge? Because it looks like the letter H. Do you agree? This one, and this one, right? Okay. So then, how can I let this guy work? How can I let this guy work? And these are two directions. And the first, I want to make sure my current can go from left to right this way. Then, if I want to change the direction, I want the current can go from the right to the left. And how can I control? I can control this PNP transistor and this NPN transistor. For example, here at this instant, I want the voltage difference between these two terminals. This is a emitter and a base. These two terminals is greater than the threshold value. Then this guy will allow the current to go through. However, I just shut off this one and shut off this one. But at the same time, I let this NPN and to allow this current to go through. So how to do that? I just make sure this is the voltage difference between the base of this emitter is greater than the threshold value, and then I will have the current go this way, going through here and going down. So this is inside of this DC motor, and the current going from the left to the right. What? So I just control, make this one turn this on and turn this on, and then the current can go through these two guys, and as a result, here I can control. I can turn this on and turn this on, and then this current goes from left to right. Hidden.
What's the difference between a PNP and an NPN transistor?
So this is dependent upon what kind of the doping element you add to the semiconductor or silicon. Both of them they use the silicon, but the doping element is different.
Do they function the same in a circuit like this?
The function is the same, but they are different. This mechanism is kind of different. We will talk about this one in our next class. But now I want you to know how this PNP and NPN works. So both of them, Aiden's question is very good. Both of them are based upon the silicon, but the doping element is different. The doping element, the P layer is UN. This is the boron. You know boron is, right? The P, UN, the boron. you add boron into this silicon. And for the N, you add phosphorus to silicon. For the N, and you add for this phosphorus. Phosphorus, so into silicon. So you need to keep in mind that the silicon itself is useless. Silicon itself is useless. You must add these doping elements. You know doping, right, guys? What's the doping? What is doping? Doping means that something that you add can substantially enhance the performance of this original things. So this is doping element boron. This is the major. This is a material. Basic material is a silicon. If we add boron, we can enhance the performance of silicon. If we add this phosphorus, we can also enhance the performance of silicon. And just as this anti-doping is committee, do you guys ever heard anti-doping committee in Olympic games or other? This is other these games, U.S. Open, tennis Open. You know that, right? You check if you have just used some illegal substance or not. The same thing. Doping, D-O-P-I-N-G. Hey, thank you very much for the question. Now it's okay? Okay, guys, so for this one, if I turn this on and turn this on, I can make sure the current in this is DC goes from the left to the right. And however, if I turn this off, these two guys, but I turn on these two guys, I can just make sure the current in my DC motor is going from right to the left. So as a result, I accomplish my goal to make sure that I can change the direction of the current. As a result, I can change the direction of the motor, rotational direction. Question so far? So these two configuration is allowed. However, here is another configuration, which is the disaster. So this one is a disaster, guys. Right? So this one, why is it a disaster? Because this is a PNP and an NPN, and they can only carry a very, very tiny voltage. And then the current will go directly from the positive V to the ground. What will happen? So these two guys will be burned. And you will smell very, very bad smell. You understand, guys? It's called short circuit. You know that, right? Short circuit means that between the power and the ground, you do not have any effective devices inside. And then the current can go through directly. That we call short circuit. So this one is, and we should do whatever we want, we can to avoid these kind of things. Otherwise, the circuit will be burned. So here is the circuit. Here is the circuit. The DC motor is a DC motor, guys. Is a DC motor. And how can we control the direction of the DC motor? And you can see, we just this outer one and outer two. We just make sure we can control, we can change the direction of these two voltage. These are two output one and output two. So, can I ask a question, guys? What are the functions of these two guys? These four guys. What kind of?
You said to handle the inductive kickback.
Yeah. What's your name?
Aiden.
Aiden. Yeah, I'm recognizing. I'm sorry. I'm kind of forgetful. Aiden, right?
Yes.
In this case, also Aiden. Okay, we have two Aidens. So look at this. These are the 4 diodes. They are used for handling the inductive kickback. So here I just give you some basic knowledge about how these NPN and TNP work. So you can see we have a base NPN, base emitter, controller, collector, and also for PNP we also have these 3 terminals: base, emitter, and collector. And so this diagram shows how they work, And this is off and on. The on means that you allow the current to go through. Off means that the current is cut off, and you should know that, okay? On means the current can go through. Off means that no current. Theoretically, no current. But practically there is some very tiny, and we just ignore it. And how can these two guys work? And for this is the NPN. You can see I told you guys, you compare the voltage difference between the base and the emitter with respect to this is the threshold value, the port 6. For here, the port 6, silicon. Write down, guys. For silicon, the threshold value is 0.6 volts. But for other germanium, this is another value. You should be very careful. So we have multiple semiconductors, silicon, germanium, and they have different voltage, the threshold value. So you need to make sure if this condition is met, we have current. Also here, if this condition met, VE minus VB is greater than 0.6, so we have current. Otherwise, no current. And then we talk about this is the pulse width modulation. Pulse width, as the name suggests, pulse width modulation means that we can change the pulse width to do something useful. And what does that mean? It means that you can look at here the pulse, the high, which is not continuously high, and this is a high, and this is low. And so we have this is a concept duty cycle. It means that how long it is high and the period of cycle and multiply by 100. So this is, you can see this one duty cycle is 80%, or this duty cycle is 50%. And we will know that as long as other conditions are the same, for this case, the average voltage will be higher. You guys agree? I said as long as other these factors the same. And for the second one, the average voltage will be higher. How it works, you can see. If we have this kind of pulse, very high, and but for a short time, and then we have another one. So here is the voltage. So here is the average voltage. So however, if we increase the width of each pulse, so as a result, so the average voltage will be high. So this guy, for this case, and we will have higher speed. And for this case, we have lower speed. So this is called the pulse width modulation. And we use pulse width modulation to control the speed of the DC motor. Now this time we are not controlling the direction of the DC motor. We are controlling how fast it goes. Right, guys? There are two different concepts. One is the direction. Second one is magnitude. Clockwise, counterclockwise. We talked about this already, and then we talk about how to adjust the magnitude of the rotational speed. So here we can just adjust. You can see. So this is 0.5 50% of the voltage, and this is 80% of voltage. Definitely, this one will give us a higher. This is rotational speed. Okay, this one on the speed control with the pulse, you can see that. So here's the duty cycle. We want to establish the relationship between the duty cycle and the RPM. RPM is the rotational speed. I can see the different, this is different frequencies, 1 kilohertz, 10 kilohertz, and 250 kilohertz. And for different, this is the speed, frequency, and we have different characteristic curve. And so this characteristic curve is usually available from the vendor on the data sheet of the components. Okay, and for this, how to select which frequency and is best, it depends upon your application. And for this one, from very beginning to very end, is almost the linearity, almost linear. From the non-linearity is from 20% and to 100%. But for other frequencies, at the very beginning, it's also linear, but so this is slope changes. So this is dependent upon on how you want to use this is the pulse width modulation. Okay, guys. So now what do we have learned today? And we have learned inductive kickback. What is inductive kickback, and what mechanisms we have and to handle this in the disaster scene. And second, how can we control this direction of the current in order to control the direction of the motor by using the NPN and PNP? And third, what is the PWM and how can we use it? PWM means pulse width modulation, PWM. So this is pretty much what we have learned today. And I hope you guys have a wonderful Wednesday. All right.